Hello and welcome to another unit of basic electrical circuits. In the previous unit we have looked at certain two terminal elements. In this unit we will look at certain elementary combination of these elements and see how they behave. And when I say how they behave, what I mean is what the equivalent characteristics of the combination is. That is, you could have a network consisting of a number of elements, but let us say only two terminals are exposed to the outside world, and inside we could have any number of elements, any element we want. Okay. Now, if we are only allowed to connect to these two terminals, this whole thing is effectively a two terminal element with some characteristics. Okay. To determine what the characteristics are, we have to find the relationship between the voltage across these two terminals and the current which goes into the terminal. Okay. So, we need to determine the IV relationship, and this could be either by algebra or graphically. Okay. They are just equivalent descriptions of the same thing. For single elements, we saw that we could either specify algebraically, such as Ohm's law, when we say V equals IR, or we could draw a straight line in the IV plane with a slope of 1 over R. Okay. Both of these correspond to a resistor. Okay. So, sometimes one is more convenient than the other, and we are going to use that one. Okay. So, first let us look at what is known as a series connection. So, this refers to series connection of two or more two terminal elements. Okay. So, for instance, we could have one resistance and another resistance and connect them in series. Now, what constitutes a series connection? For two terminal elements, then one terminal of element A connected to a terminal of the second element B. Okay, or basically, okay. Now, the important condition is that they should be connected such that the same current flows in the two elements, meaning there is a node which is common to the terminals of the first element and the second element, and nothing else is connected to this node. So, this means that by Kirchhoff's current law, whatever current is flowing in element A will also flow in element B, because they are connected to the same node and nothing else is connected to it. Okay. So, this is known as series connection. The important property is that the same current flows through them. Now, you could have a number of elements in series, okay, one after another. The point is, again, each node will have two elements connected to it and nothing else connected to it. So, the current in this element will be exactly the same as the current in the other element. This is enforced by Kirchhoff's current law. Okay, this has nothing to do with what elements we connect. Okay. Now, next what we will do is we will take the different elements that we know one by one and see what happens when they are connected in series. Okay. Now I just said that when you have a number of elements in series, the same current flows through all of them. Okay. Because of KCL at these nodes implies that the same current flows through all of them. Okay. And also the one thing you notice is that if you form a loop with something connected to this, okay, it doesn't matter what it is, and you denote this voltage across A by VA, the voltage across the element B by VB, and this is the element C, this by VC, and let's say we denote the voltage between the upper and lower terminals by Vx. Then we can write the Kirchhoff's voltage law equation around this loop as Vx minus Va minus Vb minus Vc equals 0, or Vx equals Va plus Vb plus Vc. Obviously, this means that the voltage across the ends of the series combination by series combination I refer to this whole thing here equals the sum of individual voltages. Okay. So this then is the definition of series connection. The same current flows through all the elements, and the net voltage between the ends of the series combination is the sum of the individual voltages across the elements. Okay. So first let's take the elements in the same order that we discussed them. Let's take two voltage sources in series. Let's say this has a voltage of V1 and this has a voltage of V2, and obviously we are looking at what it looks like between these two highlighted terminals. Okay. Now I will go through it perhaps more elaborately than necessary because this is the first time we are discussing it. I think all of you know the answer to this particular thing already. Okay. Let's imagine that it's connected to something, it doesn't matter what it is, and by applying Kirchhoff's voltage law around this loop, okay, so if we call this Vx between the upper terminal and the lowermost terminal, we'll clearly see that V1 minus Vx plus V2 equals 0 because of Kirchhoff's voltage law. Okay. So Vx has to be equal to V1 plus V2. Okay. So this is a very elementary use of Kirchhoff's voltage law. It says that if you have two voltages in series, the resulting voltage between this terminal and that terminal is the sum of the voltages. Okay. So in general, if you have a number of voltage sources in series, V1, V2, and I will show it all the way to Vn, the net voltage is V1 plus V2 plus all the way to Vn. Okay. So a series connection of voltage sources behaves like an equivalent voltage source, because we see that this Vx here is a fixed value. Okay, it doesn't depend on the current. The Vx is V1 plus V2. So if you have a number of voltage sources in series, the result is also an independent voltage source, and the value of the voltage source is sum of all the individual voltage source values. Okay, so this must be pretty obvious. This whole thing between these terminals is equivalent to single voltage source Vx, whose value is given by this summation. Okay. So what have we learned so far? A series combination of voltage sources behaves like a voltage source, and the value of the voltage source is the sum of the individual voltage sources. Of course, you have to sum the voltages in the appropriate polarity. Okay.